Now here's another example of a problem involving normal forces. I introduced the two-block problem the other day. So what's the first thing we do? We draw a picture. Two blocks, masses m and m. Usually a big M makes me think it's a bigger block. Are on a flat, frictionless surface. All of our surfaces are frictionless for the moment. Soon we'll learn about friction, and our surfaces will not be frictionless. The block with mass m is on. I should have read that sooner. Good thing I got lucky. That little m is on the left. The blocks are touching. Push block m to the right with force F. What is the magnitude of the force the blocks exert on each other? So, now we all know that in this situation both blocks would be pushed to the right. But what is actually pushing block m to the left? Well, you might think, oh, I am. Well, that's not entirely true. You're pushing block little m, and little m is exerting a normal force on big M. There's a normal force that block of mass little m is exerting on the block with mass big M. And by Newton's third law, there is a normal force that the block of mass big M exerts on the block of mass little m. Now, as far as we'll get to it in a second. So there are these forces that the blocks exert on each other, and that's what we're trying to find out. Okay. And to do that, we write Newton's second law. Now, there are other forces acting on these blocks. On both of them, or each of them, we have gravitational force, and we have a normal force. However, since they're on a flat surface, and they're staying on the surface, I'm pushing with a force to the right. We don't actually care about what's going on in the y direction, but, we could write normal force equals mg for each block and figure that out. So what we really care about is in the x direction. Now, with a problem like this with multiple masses, there are a couple of different ways to look at it. You could look at it as a system, or you could look at it as individual objects. Now, if we look at the whole thing as a system, then in the x direction, we have, we're always writing sum of the forces equals ma. We have this force F. It's being exerted to the right. It's frictionless. Okay. Well, we have these normal forces that they exert on each other, but forces internal to the system don't matter because if we think about the whole system, the two blocks together, then the force this block exerts on this one, that's to the right, and it is equal and opposite to the force that this block exerts on this one, which is to the left. So technically we could say plus Fnmm minus Fnmm, but then that's just going to be equal to 0. So those two forces cancel out when you consider the system as a whole, and so we don't need to worry about that when we consider the system as a whole. So for the whole system, we've got F equals little m plus big M times acceleration. Now, since the blocks are touching each other, they can be treated essentially as one object, so the acceleration is going to be constant. The acceleration is going to be the same for each block. Mass little m can't accelerate at a different rate than mass big M. If we consider mass m, there's only one force acting on mass m. It's the normal force from little m on big M, and that's equal to mass times acceleration. If we consider block mass little m, we've got the force that I am exerting on it to the right. We've got the normal force that block m exerts on it to the left, and that's equal to little m times a. Now, these equations are more information than we need. We can get all this information by using just two of these. In fact, we can use any two of these that we want to. From this point forward, it's just algebra once we've written these. But the skill that you need to learn is to be able to consider the whole system and then to consider individual objects within the system. So if I look at my system, I can see that the acceleration of these two blocks is F over big M plus little m, and that is the same thing as the acceleration of either block. So if I combine that with this equation over here, I can say that this normal force the blocks exert on each other is equal to big M times F over big M plus little m. And we could arrive at a similar result if we combine these two equations. We could add these two equations together, and then we'd get F equals, well, M plus M over A times A, which is the same thing as the system equation. So all these equations kind of all represent the system, but the magnitude of this normal force the blocks exert on each other then is M times F over big M plus little m. On the AP test, there are always a couple of questions like this, where you have to solve for some value, given only the parameters that they give you in the problem. So this acceleration is something I introduced, so it shouldn't be part of my answer. But this is a key skill, is to be able to break down single mass, one mass, two masses system, and compare them. Another important physics problem is an object on an inclined plane. So a lot of times we'll have problems where we're on a ramp, it's angled at some angle above the horizontal. We've got our object sitting on the ramp. Okay, now let's think about what forces are acting on the object. Well, it's frictionless for the moment. Next time it won't be. But there's always gravitational force acting on this object, and there's a normal force, but remember, normal forces always act perpendicular to the surface, so the normal force acts this way. All right, oops, I wrote MA, that should say MG, that is a mistake. MA should never go on a force diagram because MA is not a force. It is how we figure out the acceleration of the system or the mass or whatever. But MA itself is not, it has units of force, but it's not an actual force that is acting on the system. All right, so that's all that we've got for our force diagram. As we go along, we'll add more and more forces here. We'll have friction. We might have an applied force, and it'll get more complicated. But that's the basic situation for our object on an inclined plane. Now, in dealing with an inclined plane, how can the object move? Well, it's not going to fall through the plane. It's not going to jump off of it, right? So the acceleration is always parallel to the plane. And because the acceleration is in that direction, going this way or this way, it is convenient to rotate the coordinate system. Generally speaking, we will rewrite our axes. We'll call the y direction the direction that is perpendicular to the plane. And the x direction is the one that is parallel to the plane. These are just conventions. You could call this way x and this way y if you wanted to, but I'm going to stick with this standard, and I will generally call the positive x direction down the plane. Right? So an object of mass m placed on a frictionless plane, inclined at theta above the horizontal. If you recall, we did this lab back when we were doing 1D kinematics, and I told you then that the acceleration is equal to g sine theta. Well, now we'll see why that is. So, mass m, frictionless inclined plane angled at theta above the horizontal. All right, well, let's do some stuff. There is going to be no acceleration in the y direction, but I'm going to write Newton's second law in both directions. The y direction will become important when we add more forces later on. So in the y direction, what do we have? We've got a normal force, and that's just straight up in the positive y direction. But now, with my rotated coordinate system, gravity is not going straight in the y direction. It's not going straight in any direction. So we need to split it up into components. Okay, now this is mg going straight down. I'm going to draw it bigger out here. The component parallel to the ramp would be this way, more or less. The component perpendicular to the ramp would be this way. Okay, now looking at our triangle, if we look over here, if this is theta, that means this angle right here, which is this angle, is 90 minus theta. which means that this angle is also theta, because it is complementary to this one. So if this angle is theta, that means that the sine of theta would be this component over mg. So this is mg sine theta, and this would be mg cosine theta. Now this is a departure from our standard with vectors. In this case, because of how the angles are and how we rotated our coordinate system, the x component of the gravitational force is mg times sine of theta, and the y component is mg times cosine of theta. That tends to throw people off, so be aware of that. So we've got normal force going in the y direction. Well, the y component of this is going into the plane. It's going into the plane. That's the opposite direction, so that's minus mg cosine theta. And this thing is just going to chill out on the ramp, so in the direction perpendicular to the ramp, the acceleration is 0. So the normal force acting on the object is equal to mg cosine theta. We'll use this result when we talk about friction a lot. Now, it's not relevant to the answer to this question, but it's good to know. In the x direction, what forces do we have in the x direction? Well, we just have this component of gravity. We have mg sine theta. That's equal to mass times acceleration in the x direction. And you may notice mass cancels out, and we find the acceleration is equal to g sine theta, which is exactly the result I had you use for the lab. I should have mentioned this when we talked about gravity, but this is exactly why, like when we do kinematics, the acceleration due to gravity is not dependent on mass, because the gravitational force is proportional to mass, but the acceleration is inversely proportional to mass, and so those proportionalities cancel out.